Okay, let's see if we can demonstrate how to do these vector problems. Let's say we've got an angled vector going that way, and I'm just making this up as I go. And then let's say we have another vector going straight down, and another vector maybe going slightly at an angle over this way, maybe that big. And let's say that they all interact, and we're going to figure out what happens. Like, I guess you could imagine if three pickup trucks were pulling another truck out of the mud, and they all pulled in this fashion, this truck pulling this hard, this truck pulling that hard at an angle, what would happen? Which way would the force, the net force, actually go? Because as you may realize already, if these trucks pulled like this, they probably wouldn't be a very good arrangement because they would cancel each other out a lot. But here's how we figured it out. Let's start with this angled right here. Now this one can be thought of as if the sun was going down and it was over here, its shadow on the wall would be right like so. And then if the sun was straight up, its shadow on the floor or on the ground would be like so. So now that we've represented these as their vertical and horizontal, or not these, but this one, I'll just erase it. Let's get rid of it. It's no longer there because it's being represented by the vertical and horizontal vectors that I just drew. So now if we can just break this up into its X and Y components, then the game will be pretty simple. Solving what they do will be very easy. So here's this one's X component, and this one's, once again, I'm imagining if the sun was going down and it cast its shadow on the wall, it would be about so big, a little bit shorter than this one right here. And since they're occupying the same space, I'm just going to kind of draw it a little off to the side here. So we've got two arrows going on right here. So now that this one's been broken up into its X and Y components, we can get rid of it. So now you see it's actually rather simple, because these guys are directly fighting those guys, these guys are directly fighting these guys. In fact, this arrow, this one, the longer one, looks like it's about the same and opposite direction as that one. So I'm gonna cancel both of those. I'll just erase that and erase this one. And it's important to know that there's still one there, because remember I drew it right next to the other one. So we end up with this and this. That means this much. I don't know, if we wanted to be super accurate, we could say 2 centimeters of this one's gonna get canceled out. So its new length will be like that. So this much gets canceled. This right here cancels that much over here. So we can get rid of this and get rid of that. And now we're reducing down to a very simple situation where we just have this contributing to that. And since X components have no effect on Y components, like they're independent, we pretty much just have to calculate the result. The result is, if you imagine a dotted line like that, a dotted line like this, where those two intersect is where the resultant would be. Because that's how you would break this up if you went back the other direction. If I gave you this angle, you'd say, okay, its shadow on the wall would be like that, and its shadow on the floor would be like that. So this is the result, and since it represents this and this, there it is, that's the result. And if you remember, we started out with 3 trucks pulling, one truck pulling this way, one pulling that way, and one pulling that way. The net result of all those trucks pulling on this object would be as if one truck only pulling this hard was pulling in this direction. And that makes sense because there was a downward force and an angled force. There were 2 forces in this direction and only one going that way, and it was, you know, canceling out in some respects what was going on there. But that's how you solve these problems, and it's actually quite simple if you just break them up into their X and Y components.